Recycling bitumen from dismantled road. A case study. Abstract. In a developing country like India, many changes in urban planning and infrastructure facilities are proposed and brought into practice on a daily basis. One such commonly faced challenge is the proper handling of demolished pavements during road construction and rehabilitation. Also, if the demolished pavement is not disposed of in the correct manner, it may cause serious environmental hazard. A possible solution to this is the reusing of demolished materials by recycling in proper manner. The solution, not very commonly adopted in India, may become a possible alternative for pavement construction for the current ambitious road building program underway. The present study involves the recycling of existing asphalt pavement materials of a dismantled road at Indore, India, to produce new pavement materials. The results showed considerable savings of material, money, and energy. Keywords: infrastructure, pavement, recycling, environmental hazard. Introduction. Over the years, recycling has become one of the most attractive pavement rehabilitation alternatives in developed countries. Unfortunately, asphalt pavement recycling is yet to take off in India despite the current ambitious road building program underway. Recycling of existing asphalt pavement materials to produce new pavement materials results in considerable savings of material, money, and energy. The specific benefits of recycling can be summarized as follows. A. Substantial savings over the use of new materials. B. Conservation of natural resources. C. Performance equal or even better than new materials. D. Pavement geometrics is maintained, and E. Saving of considerable amount of energy compared to conventional construction techniques. The last benefit is very important due to the recent urgent need for reducing greenhouse gases, that is, reducing carbon footprint, thereby earning carbon credits for India. The Asphalt Recycling and Reclaiming Association define 5 different types of recycling methods: 1. Cold planning, 2. Hot recycling, 3. Hot in-place recycling, 4. Cold in-place recycling, and 5. Full-depth reclamation. Only hot recycling of asphalt pavements at a central plant will be discussed in this article in the context of 4-laning and 6-laning of India's state highways and national highways, wherein road paving bitumen worth crores of rupees is being buried rather than recycled. Literature review. Arvind and Das, 2006. Adopted central plant hot mix recycling for recycling of asphalt pavement materials. Literature review reports varied levels of performances, laboratory as well as field, of recycled mix compared to the performances of corresponding virgin mixes. Thus, they conducted performance-related tests before finalizing any recycled mix design. They conducted laboratory study on recycled mix design of 2 different reclaimed asphalt pavement, RAP, samples, and subsequently developed an integrated mix design structural design approach for hot recycled mix. The total cost of the asphalt layer construction was estimated considering the constituent proportion and the pavement design thickness so that the designer may choose the best option. Shanyashri, et al. Proposed that recycling of asphalt pavements is one of the effective and proven rehabilitation processes. For the laboratory investigations, reclaimed asphalt pavement, RAP, from NH4 and crumb rubber modified binder, CRMB 55, was used. Foundry waste was used as a replacement to conventional filler. Laboratory tests were conducted on asphalt concrete mixes with 30, 40, 50, and 60% replacement with RAP. These test results were compared with conventional mixes and asphalt concrete mixes with complete binder extracted RAP aggregates. Mix design was carried out by Marshall method. The Marshall tests indicated highest stability values for asphalt concrete, AC, mixes with 60% RAP. The optimum binder content, OBC, decreased with increased in RAP in AC mixes. The indirect tensile strength, ITS, for AC mixes with RAP also was found to be higher when compared to conventional AC mixes at 30 degrees C. Thus these previous studies were referred to before conducting the tests in this study. Methodology. A sample of the bituminous layer was collected from the dismantled road at Malva Mill area in Indore. The sample was broken into small pieces, washed with water and then dried for 1 day. An amount of 250 grams of the washed sample was taken out for performing the bitumen extractor test to determine the initial bitumen content. Aggregates of different sizes were purchased from the market. Sieve analysis was performed on each sample of the aggregates procured from the market. Grading of material was done according to Section 509 of MORTH, Ministry of Road Transport and Highways, Code. Samples of different grades of materials were then weighed, 1,200 grams each. Aggregate sample was then heated up to 160 degrees Celsius and then cooled up to 140 degrees Celsius in a pan. Another sample of heated bitumen grade of 60 to 70 was added to the heated material and then mixed. Mold was prepared with varying percentages bitumen content. Marshall stability test, Figure 1, was performed for each sample having different percentage bitumen content to determine stability and flow value, voids in aggregate, VA, voids in mineral aggregate, VMA, and voids filled with bitumen, VFB, as given in MORTH. Marshall stability test was preformed for these samples to determine stability and flow value. Stability and flow value of each sample was compared. Result analysis and cost analysis was done. Conclusions were derived from the same. Results. Sieve analysis on aggregates 4.75 mm, 6 mm, stone dust, and cement were first performed in the material testing laboratory as prescribed by Indian standards. As an example, a sample table for sieve analysis of cement is given below in the form of Table 1. According to IRC 29-1968 specifications, the mineral aggregates including mineral filler should be so graded or combined so as to conform to the grading. Unless otherwise specified, for compacted layer thickness of 24 to 40 mm, any of the two grading can be used, but for layer thickness of 40 to 50 mm, only grading number 2 can be used. Table 2 gives the aggregate gradation for bituminous concrete. First, the initial bitumen contained for the sample was calculated by bitumen extractor. Then the optimum bitumen contained by Marshall stability test, and finally the required bitumen to be added in sample was calculated. Table 3 gives the results of sieve analysis for bituminous concrete. The obtained bitumen mix was compared with the standard requirements and the results of the same have been summarized in Table 4. Also, a clear comparison between old sample and new sample has been given in Table 5 for two parameters, viz. Stability and flow for different bitumen content. Also, the variation of strength and flow parameters with varying bitumen content has been further indicated graphically in Figure 3 and Figure 4 respectively. The density of the sample, G, was found to be equals 2.44. The specific gravity of the total blended mineral was calculated after determining the specific gravities of different aggregate used in the mix. Providing and laying bituminous concrete with hot mix plant using crushed aggregates of specified grading, premixed with bituminous binder, transporting the hot mix to worksite, laying with a mechanical paver finisher to the required grade, level, and alignment, rolling with smooth-wheeled vibratory and tandem rollers to achieve the desired compaction in all aspects and as per clauses of Section 509. Only cement will be used as filler. Conclusions. Cost of construction of bituminous concrete layer of 100 meter length, 7.5 meter wide and 4 centimeters thick, quantity 30 cubic meters, is 246,780 rupees only, while recycled dismantled road cost is 74,893 rupees. Thus a saving of around 70% is observed in cost incurred when recycled bitumen is used as a partial substitute of fresh concrete. The stability as well as flow values were found to be increased for new sample. It was found experimentally that around 70% of the bitumen of the dismantled road may be recycled and used for further pavement construction activities. This may also serve as a lucrative option for the disposal of bitumen for dismantled roads. As bitumen resulting in dump yards poses a serious threat to the environment, Recycling of this bitumen can protect mankind from this ecological hazard. Acknowledgement. The authors wish to thank Director and staff of Prestige Institute of Engineering Management and Research, Indore, for their technical support during the tests performed in the laboratories in the Civil Engineering Department of the Institute.